So the last thing that we really haven't talked about is how salts affect water. We've talked about strong acids and strong bases, weak acids and weak bases, but salts kind of get a little bit tricky, so pay attention. So the first thing I want to look at here is let's put some salts into water and what happens to the pH when I put salts in water. We know that acids will lower the pH, we know that bases will raise the pH, and at this point we've been led to believe that salts, because they don't contain hydrogen to make hydronium, won't shift the pH, and because they don't contain hydroxide, they also won't act in a basic function. So here I have a little video for you of a demonstration that we did today in class. Let's play this little video. First thing I'm doing is setting up each of these beakers just with some distilled water. Next, I add in a little universal indicator. I'm going to stir up each beaker just to try and make sure that the color is well distributed. So into the first beaker, I'm going to add in just a little bit of sodium chloride, just plain old salt. Mix it up, and if you'll notice, absolutely no color change. We are smack dab right in the middle, neutral pH. Science isn't broken. Yay. Into the second beaker, I'm adding in a little bit of sodium acetate. Shock! Blue! Oh my goodness! So the pH shifted blue according to the pH scale that we have with the indicator chart. Into this beaker, I'm adding in sodium phosphate, Na3PO4, extremely basic, and yet the utter definition of a salt. This is Na2HPO4. So still basic, but not quite as basic. Kind of interesting. NaH2PO4, and if you'll notice with this one, immediately a pink color appears, clearly shifting dramatically in the acidic fashion. Sodium hydrogen carbonate instantly turns a really cool teal color, slightly basic. Aluminum nitrate, this is one of my favorites. Extremely acidic. Ammonium chloride. slight shift here, again to the acidic side, probably somewhere between 5 and 6. And into the final beaker, some potassium carbonate. Gorgeous purple color. So again, just kind of an up close shot here. There's your sodium chloride and your sodium acetate. So what is happening here? Well, first we know that when the salts go into the water that they first have to dissociate. So here you have solid sodium chloride dissociating into its two aqueous ions, sodium and chloride ion. Well, the next thing that we need to start thinking about is how these ions themselves are interacting with the water. Well, if the sodium does in fact interact and react with the water, it's going to try to do one of two things. Of course, there's two kind of driving forces in chemistry. Number one, make sure that everything has an octet. And after your octet is fulfilled, then make sure that you're also neutrally charged. Na1+ already has its octet, but it is not neutral. So when it interacts with water, its main goal is to try and bring its overall charge back to neutral. In order to do so, it's going to steal a hydroxide ion out of the water, potentially forming sodium hydroxide and hydrogen ion. So if sodium reacts with water, it's going to form hydrogen ion in water. In other words, essentially acting like an acid. Chloride ion does much the same thing. It's just that instead of taking a hydroxide ion, it's actually going to pop off a hydrogen ion to kind of, balance out that -1 charge. And this would generate hydroxide ions in solution, creating a more basic shift in the pH. Unfortunately, just for plain old NaCl, we didn't see a color change with the universal indicator. That means that neither the Na nor the Cl is interacting with water in this fashion. And the reason for this is that in order for this reaction to take place, NaOH or HCl would actually have to form. We identify these as both strong acids or strong bases, which means as soon as they would form, they would immediately dissociate in water. In other words, they never actually form in water. So neither of these reactions actually happen. Thus, no shift in the pH. That's not the case with all salts, however. So again, just kind of summarizing our results here. The Na does not react with water, no net effect to the pH. Cl does not react with water, no net effect to the pH. But what about if we had a different kind of salt, like potassium hypochlorite? Again, that would dissociate into potassium and hypochlorite. The potassium, if it reacted with water, would steal a hydroxide to neutralize its charge and become potassium hydroxide. Well, potassium hydroxide is a strong base. That's not going to form, therefore there's no reaction and no effect to the pH. Hypochlorite, however, if that reacts with water, would steal a hydrogen to become neutral, forming hypochlorous acid. That is a weak acid. It doesn't immediately dissociate, therefore actually will form in the solution. So this anion from the salt reacts with water to create a weak acid. In the process of doing so, also will make some free hydroxide ion in the solution, and will shift our pH dramatically to that basic side, and will turn a universal indicator that bluey purple color. Well, what about something like ammonium nitrate? Well, again, it will dissociate into ammonium and nitrate ions. The nitrate itself, if it would react with the water, would pull off a hydrogen and form nitric acid. Since that's a strong acid and would immediately dissociate anyway, there's no reaction, no effect to the pH there. However, the ammonium ion, if that reacts with water, would actually donate a proton to that water, forming hydronium ion and ammonia. That ammonia, since that is a weak base, actually legitimately forms. So we will get some free hydronium ion in the solution. This will decrease the pH and shift the color of the universal indicator more to the red side. And how about this beauty? We have ammonium hypochlorite, so we've kind of got two ions here that could interact with water. The ammonium is going to make some hydronium ion, the hypochlorite is going to make some hydroxide ion. Well, we have a decision here. How are we going to decide which direction the pH is actually going to be shifting? That depends on which of these two species acts in a stronger fashion. And how are we going to be able to determine that? Well, that's by comparing K values. So up next is going to be, how do we calculate a K value for an anion or a cation? Because I'm not sure if you've taken a look yet, but if you look at your K chart, you will not find a K value listed for an anion or a cation. They're all just acids and bases. So that's up next. Of course, once we establish what these K values are, if we find that the Kb is about equal to the Ka, there shouldn't really be any net change to the pH at all. If we find, however, that the Kb is larger than the Ka value, then that means that the base component is a bit stronger. The pH should shift higher and therefore act kind of more like a base. If the Kb, however, is lower than the Ka value, then that means that the acid component is stronger. The pH should drop, and our indicator, of course, would turn red.